So radical expressions. Radicals are roots. So a radical expression is any expression with a root in it. So for example, the square root of x. Square roots behave a lot like powers because they are. So the square root of x is the same as x to the power 1/2. So a quick example of that relationship. If I had the square root of 9, you might recall that 9 is 3 times 3, so 3 is the square root of 9. But I can just play around here a little bit with powers and this idea of a square root being power 1/2. So 9 is 3 squared. So what I really have here is the square root of 3 squared. The square root is really the power 1/2. And inside I have 3 squared, and parentheses are necessary here. You might remember a rule from earlier in math that if you have a power to another power, you multiply those powers. So this is 3 to the second power times 1/2. So 2 times 1/2 is in the power, and 2 times 1/2 is 1. 3 to the first power is 3. So just an example of the idea that a radical expression can be written as a power. Similarly, if I had, for example, the 5th root of, say, x, that would be the same thing as x to the power 1/5. So we could check on a calculator. If x was, say, 32, what is the 5th root of 32? And give that a shot when you get a chance. You can either use a root button if your calculator has it, or use the power 1/5. So in some calculators, I might enter that as 32. Oops, that's not a 2. Raised to the power, I might have to use some kind of power button, and then sometimes I'm going to need parentheses. 1/5. So it's good to know how to use your calculator for powers. So let's take a look at some other ideas. A lot of what we're going to be doing here are simplifying radical expressions. So for example, the square root of 9 can be simplified to be 3. The square root of, say, 75, it's a little more complicated. If I do a factor tree on 75, I can see what factors there are. So let's see, 2 doesn't go into 75. 3 does go into 75 because 7 plus 5 is 12, and 3 goes into 12. So 3 goes into 7 twice with 1 left over, and 3 goes into 15 5 times. So 3 goes in 25. You can verify that on a calculator if you need to. And then 2 doesn't go into 25, 3 doesn't go into 25, but 5 goes into 25 5 times. And anytime in a factor tree I find a pair of factors, then I get to pull it out. Square root of 25 is 5. So I could rewrite this in a couple of different ways. I could say this is 5 times 5 times 3, and the square root of 5 times 5 is just 5. The 5 pops out, leaving the 3 behind. So if a factor ends up being repeated, it comes out. Let's try another one. Suppose we had square root of 32. So if I do a factor tree on 32, let's see, it's even. So 2 goes in there, 16, still even. 2 goes in there, 8, still even. 2 times 4, and then 4 is 2 times 2. And again, every time I have a pair of factors, 1 pops out. So there's 1 pair. So a 2 is going to pop out. There's another pair. So another 2 is going to pop out. And then this one's all by itself, so it's stuck inside the root. So the square root of 32 seems to be equal to 4 times the square root of 2, and we could verify that on a calculator. Plug into your calculator, square root of 32, plug in 4 times square root of 2, and they should be equal to one another as a decimal. All right, so let's play with some variables. Oftentimes we want to reduce a square root, which means pull out perfect squares. Sometimes it's got some more complicated meanings that we'll see in a minute. So suppose I had the square root of 175 times z to the power 13. So we probably want to break down the 175 first. And let's see, 1 and 7 is 8, plus 5 is 13. So 3 doesn't go in there. 5 goes in there because it ends in a 5. So let's see, 5 goes into 17 3 times with 2 left over. 5 goes into 25 5 times. So 5 times 35 is 175. You can check on a calculator. 5 still goes into that 7 times. So it looks like 175 is 5 times 5 times 7. We can verify that on a calculator. Might be a good idea to do that. Let's get a calculator out. So 5 times 5 times 7 is indeed 175. Now the z, there's a few ways to do that one right there. We could break down z into a whole bunch of z's. That's going to be 13 of them. Now that's kind of a lot of work. I really don't want to write down 13 z's. Remember that a square root is the power 1/2. So z to the 13th inside a square root is the same thing as z to the 13th to the power 1/2. Power to a power means multiply, so that would be z to the power 13 times 1/2, which is 13 halves. And then think about 13 halves for a minute. 2 goes into 13 how many times? Well, 2 goes into 13 6 times. 6 times 2 is 12, and I get a 1 remainder. So again, a square root is looking for a pair, right? And that's what this 2 down here is, just looking for pairs of z's. And we found 6 pairs of z with 1 left over. So from the z to the 13th, 6 z's get to pop out, just like the 2 5s mean 1 5 pops out. So I should be able to rewrite this as 5 pops out. Z to the 6th is going to pop out because there are 6 pairs of z's in 13. And then inside should be a 7. We didn't get to pull that out. And there was 1 extra z according to that right there. So the square root of 175 z to the 13th should be equal to 5 z to the 6th times the square root of 7z. How could you check that? Well, we got here by just using properties of what it means to be a square root. And that means you have to have a pair of multiples inside for 1 to pop out. The only way to really check it is to do it again without looking and hope it comes out the same, or pick a number for z and plug it in. So I could check by evaluating. And so then I just pick some number for z. Avoid picking numbers like 0 and 1. They can be misleading. So I might pick z equals 3. And usually with square roots, we pick positive numbers because negative numbers lead to imaginary numbers. So if I plug in a 3 here and a 3 there, I hope I get the same result. So let's give it a try on a calculator. So on my calculator, I would start my roots, and then I would have 175 times, instead of a z, I'm plugging in a 3, and it's raised to the power 13, close the parentheses, and I get 16,703 point blah, blah, blah. So we'll bring up another calculator. And this time we'll type the other way. So the other way, let's see, we pulled out a 5 times z to the 6. So that would be 3 raised to the 6th power. And then, I guess let's get that started on the computer because we need that square root button. If you don't have the square root button, like in a web browser, you can actually type sqrt and the computer will recognize that as a square root. And then inside I had 7 times z, which is 3 here. So we'll just double check that. And let's see, that looks like the same number I had before. Perfect match. So just double check here. I'm entering the second version to see if it matches with z equals 3. And so that would be 5 times z equals 3 raised to the power 6 times the square root of 7 times z equals 3. Close parentheses, and I get the same number as before. So just because it checks for one number doesn't mean it will check for all, but it's a good start. So this is leading me in the right direction. It seems like this is a check on my calculator. All right, let's try another one. Suppose I needed to reduce a fractional root, so 18x cubed over 5, and we'll take the square root of that. So similar to before, I got to see what breaks down here, and so making a factor tree for 18, 2 goes into 18, 9, 9 is 3 times 3, so I get a pair of 3s that are going to pop out. So right away I can say, okay, 3 pops out. X cubed, well, a cube has a pair of x's with 1 left over. So one of those x's will pop out, right? The x squared, one of those pops out and leaving that x behind. So I'm going to get 1x out. And let's see, inside at the moment, I'm going to have a 2 and an x. So, and we still have a denominator. So we have a 2x and we have a 5 in the bottom. So here's where I am so far. The 3 times 3 popped out as 3. The x times x here popped out as an x, and then we're stuck with a 2x inside and the 5. Often we don't want roots in the bottom, and this is an idea called rationalizing the denominator. So I can rewrite this as 3x times the square root of 2x over the square root of 5. And the way to get the square root of 5 out of the bottom is to multiply by square root of 5 top and bottom. Square root of 5 times the square root of 5 is just 5. The roots cancel because I have a pair of 5s multiplied. And the top, I still have a 3x. And now, since these are the same type of root, a square root, I can bring them together. So 2x times 5 inside is going to be a 10x. So this would be a simplified version of the original one. And this extra step I applied from here to here is called rationalizing the denominator. And it's called rationalize the denominator because to rationalize means to make something a whole number or a fraction. And before I had a root in the bottom, and a root is not rational for the most part. Let's try another. How about something a little more complicated? 75x to the power 3 over y, all inside the root. So kind of similar to the problem we had before, but I have a y in the bottom instead of a 5. Not too much different though. So we'd have to break down 75, and let's do 5 this time. 5 goes into 75, how many times? 5 goes into 7 once with 2 left over. 5 goes into 25 5 times, so 15, and then 3 goes into 15 5 times, and I can say I have a pair of 5s that are going to pop out. And this x cubed is really x squared times x. So the x squared says pop an x out, but there's an x stuck inside. So I'm going to have a 3 and an x stuck inside. So 3x, and the y in the bottom is still stuck inside. So I'm at this stage right there. Rewriting this again, I'm going to break the square root apart on division. So I'm going to get 5x times the square root of 3x over the square root of y. There's an x there. And the trick I pulled before was to multiply by the square root, same square root in the bottom. So square root of y top and bottom. Square root of y times the square root of y is the square root of y squared, which is just y. Y in the bottom there. In the top, the 5x is just hanging solo up there times, since these are the same type of root, I can multiply them. So 3x times y is just 3xy, and that's stuck in the root. So then this right here would be my reduced answer with a rationalized denominator, meaning there's no roots in the denominator. All right, moving on, let's play a little bit more with the idea of a fractional exponent. Suppose we had x to the, how about 3/7 divided by x to the power 1/4. So I could rewrite this as roots. So that would be the 7th root and the 4th root here, but that's not going to make my life any better. What I can do is remember that there's a power rule that says if you have a variable to some power divided by the same variable to any power, then you keep the base, ditch the fraction, and subtract the exponents. So that's a rule from way back. So this would become x to the power 3/7 minus 1/4. So now I just have to figure out what 3/7 minus 1/4 is. So off to the side, a little scratch paper. We need a common denominator, and the quickest denominator here would be to just multiply 4 times 7 and say 28 is the denominator. So that means I also have to multiply 4 times 3 to get 12 and 7 times 1 to get 7, and we are subtracting. 12 minus 7 on a good day, I think would be a 5, and we have a 28 in the denominator now. So I've just rewritten this as x to the power 5 over 28. So that's a rational power. So I've definitely reduced that. There's only one x instead of 2, like before. And one last problem on playing with radicals. Suppose we had the square root of x plus 3 times the square root of x minus 5. When we start mixing addition and subtraction with multiplication of radicals, things get a bit more complicated. In this case, what I can do is do some distribution. So this 3, for example, has to be multiplied by both the square root of x and the 5. And this square root of x has to be multiplied by that square root of x and that minus 5. Right, so I have to distribute. So square root of x times the square root of x. I'll just write it that way for a moment. And then we're going to have the square root of x times negative 5. So that'd be minus 5 square root of x. Then we'll have 3 times the square root of x, and that's a plus 3 times the square root of x. And then we have 3 times negative 5, which is negative 15. What else can I do? Well, these guys right here are like terms because they have the same variable to the same power. So I have minus 5 of them plus 3 of them. So net, I have minus 2 of those square roots of x. And the 15 is just hanging out. Here I have a square root times itself, which cancels the root. So that's just x. And so this would be the reduced version of that product up there, which is the distributive property. And my distributive property is missing an E. Cool. All right. Hope this was fun and entertaining and useful. Take care and do good math. I'll see you soon.